have the velocity? Do we have the velocity? Negative 32t plus a constant c. We know that v of 0 is 64. 4 is c is 64. So v of t equals negative 32t plus 64. Now we want to find s of t. How much is s of t? Yes, because it's t squared over 2. Negative 16t squared plus 64t plus c1. But we are told that s of 0 is 6. 0, 0, so then c1 must be 6. So s of t, negative 16t squared plus 64t plus 6. And this is the unique function that complies with the given conditions. I think we have got the picture of how to determine these antiderivatives and how to determine the constant, and I hope so. So let's look at one more example here. Find the equation of the curve passing through 4, 2, whose slope function is given. So we are given f prime of x, which is 1 over x squared minus the square root of x. Of course, I'm going to change that into x to 1/2. And we are given the point 4, 2. Find the equation of the curve, or the function, passing through 4, 2, whose slope function is f prime. Any suggestions on how to address this? Find the antiderivative, very good. And I have to use the notation f of x. I need to find a function whose derivative is 1 over x squared. And that's one of the reasons why I tortured you a long time ago with this formula. What function prime is 1 over x squared? Very good. Yes, because 1 over x prime is negative 1 over x squared. When we differentiate negative 1 over x, we'll get 1 over x squared. Excellent. So minus x to 1/2 plus 1. 1/2 plus 1 is 3/2. Over 3/2 plus a constant c. Okay. But we are indirectly given a piece of information that will, let me simplify it first. So negative 1 over x minus 2/3 x to 3/2 plus a constant c. Yes. So 4, 2, excellent. So 4, 2 means that f of 4 is 2 indeed. That's what 4, 2 means. Very good. Excellent. Yes, you're right. Very good. So then I plug in 4. Negative 1 over 4 minus 2/3. 4 raised to 3/2 plus a constant c equals 2. Excellent. And I have to solve this equation for c. Okay. How much is this? This is basically the square root of 4 to the 3rd. Or is the square root of 4 everything to the 3rd? Yes, it is. So the square root of 4 is 2, 2 to the 3rd is 8. So this quantity is 8. So negative 1 over 4 minus 16 over 3 plus c equals 2. And I will move these to the other side. Plus 1 over 4 plus 16 over 3, Find the least common denominator, 12 and 3 and 4. I know you can do this, so that's 24 plus 3 plus 64. So 64 plus 24 is 88, 91. So C equals 91 over 12. So the function whose derivative is this, and the function that passes through 4, 2 is the unique function f of x equals -1 over x minus 2/3 x to 3/2 plus 91 over 12. I think we worked enough on this, and I would like to continue. I know we have about 40 minutes left, so we'll do whatever we can from the next section. Any questions for me? Any questions? Any questions? Okay. Here, before we even talk about areas and distances and so on and so forth, we have to identify and talk about this notation. It's a very important notation. And then I would like to work on these problems. And then we'll look at these theorems. And eventually, we'll get to where we're going. So bear with me. Okay, so this is chapter 5. It only has 5 sections, and I'm hoping to be able to finish those sections in timely fashion. So integrals. We're not talking about integrals just yet. We have a lot of preparation till we get there. So I'm not going to even define them at this point. So first we're going to look at a sum of terms. So let's say I want to write 1 squared plus 2 squared plus 3 squared plus ... plus n squared. There is a very elegant or mathematical way of writing this condensed. And this letter is a Greek letter. It stands for S. So it's our S. But we are using the Greek letter S. And it stands for sum, of course. So this is the sum from I equals 1. That's the lower limit. How far am I going? From I equals 1, how far am I going till I is n? So from I equals 1 through n, 1, and then 2, and then 3, and I stop at n. But you're right, Ian, some limits, some summation notations go to infinity. And of I squared. So this signifies this. It's a replacement of 1 squared plus 2 squared plus 3 squared plus ... plus n squared. Now, I would like you to tell me how to write this. Using the summation notation. That's it. So that's the elegant way of writing 1 to the third plus 2 to the third plus 3 to the third plus ... 15 to the third. You got it. So coming back to our handout. 1 is the lower limit. So this is called the summation notation. Here I have a different general term. I have AI. So let's write it before, let's expand this. So I equals 1 through n from a term that is AI. Okay, what will be the first term? No raised. A1 plus dot dot dot. Notice that there are only exactly 3 dots, not 2, not 4. Plus, what is the last one? AN. Very good. So again, this is the summation notation. Stands for the Greek letter S, or the sum. It's a much better notation than this would have been. We could have not write here I equals 1 to n from I squared, for example. This is more convenient notation, the Greek letter S. Good. Coming back, where 1 is the lower limit, and n is the upper limit, of course. So these are all finite sums because I have n. So these are all finite. They end somewhere. They are not infinite. Okay. So let's take a look at this, and then we'll conclude about these theorems in a minute. So if I have, all these are preparation for what follows in this chapter. So that's why we need to go through these steps. I equals 1 through 4 from 2i plus 3. So the first term, you will write 4 terms, correct? Correct? What will be the first term? Don't calculate it. I just want everyone to see it. 2 times plus 3, then 2 times 2 plus 3, then 2 times 3 plus 3, and then 2 times 4 plus 3. And then I will determine this number. However, in the same way, like we did with the limit, so do you remember when we have, for example, the limit as x approaches 4, let's say, from 2x plus 3, I can write 2 times the limit of x as x approaches 4 plus the limit of 3 as x approaches 4. So I can separate it in the same way here with the summation notation. So this is the same with the sum of 2i plus the sum of 3 from I equals 1 through 4, from I equals 1 through 4. And then I can put the factor in front, 2, the sum from I equals 1 through 4, plus 3 times the sum of 1 from I equals 1 through 4. Instead of going through term by term and then find the final answer, which will be the same, it's easier to do this and say 2, and in parentheses, 1 plus 2 plus 3 plus 4. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Plus 3 times 1 4 times. 1 plus 1 plus 1 plus 1. So this is 12. So this is 20 plus 12, which is 32. If you calculate this, you will get exactly the same number. So let's jump for a second to the first theorem. So the sum of a generic term plus another generic term is nothing else but the sum from I equals 1 through n from the first generic term plus or minus the sum from the second one from 1 to n. Exactly the same thing. And we use this. We also use the second one. So this is a constant k times ai. How will I rewrite this? K goes in front as a factor, the sum of ai, from I equals 1 through n. This is what we just did here. I had 2i, 2 went in front, like with a limit. The limit of 2x is 2 times the limit of x. Same kind of property. And this one, again, is k times the sum from I equals 1 through n of 1. So if I add 1 n times, what do I get for this? 1 plus 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 1 n times. What should this equal to? If I add 1 3 times, I get 3. If I add 1 10 times, I get 10. If I add 1 n times, I get n. So coming back here, what will you say the sum of I when I goes from 1 through 4 is? So it's 1 plus 2 plus 3 plus 4, which is 10. Right? And this one is 3 times the sum of 1 from I equals 1 through 4. But when I sum 1 4 times, I get 4 times 3, 12. So once the summation notation was invented, a lot of theorems came rushing. The sum of two generic terms, the sum of a constant times a generic term, and so on and so forth. Any questions here? I would like to determine this. 1 minute. And then these we can talk about. I don't have to do the calculator right now, but I would like to move on to these. Okay, so the calculator can wait. So I would like us to work on this for a minute. Now, I can be J. It doesn't matter. So don't think that I is the only letter that can be used for the index. It doesn't have to be. Can anyone dictate the first step? Now I would like you to use the theorems and dictate what you would write. Yes? 5, the sum of j going from 1 through 4 of j, minus 2, the sum from j equals 1 through 4 of 1. It's 2. There is no j, right, of 1. So then the first one is 5 times 1 plus 2 plus 3 plus 4, which is 10, minus 2 times 1 plus 1 plus 1 plus 1, which is 4, right? I'm adding 1 4 times. So this is 50 minus 8, which is 42. Any questions? Okay. We can prove, and you can choose, and we can do that, the following. This one we know. We already discussed this several times. How much is this? N. Very good. Now the sum of I from I equals 1 through n, we can prove any of the next three if you want, is n plus 1 divided by 2. And yes, we have to remember this one. All these four have to be remembered. 1, 2, 3, and 4. The sum of I squared from I equals 1 through n is n plus 1, 2n plus 1 over 6. And the last one, the sum of I cubed, I equals 1 through n, is n plus 1 divided by 2 is like this one, but everything squared. We can use mathematical induction and prove any of these. So if you feel like it, we just say it and we can prove it. If not, we're going to use them in what follows next.
Do we have to prove it on the
No.
You just have to do it.
You just have to know all these four. So, no proof? No. Okay, very good. Okay, so what we know so far from this chapter? You can say not much, and I will have to agree. We learned something about a notation. We learned what it means. We learned what the lower limit is and what the upper limit is and what the generic term is. And we learned how to use basically three theorems in which I have the summation of two terms, generic terms. I have the summation of a constant times a generic term. And plus or minus, of course, here I can have plus or minus. And how to find the summation of 1. Okay. Now, I got really hit with these four different concepts. So, what does this mean? Well, it means 1 plus 2 plus 3 plus dot 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 plus n. What does this mean? Well, 1 squared plus 2 squared plus dot 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 plus n squared. What does this mean? Is 1 cubed plus 2 cubed plus dot 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 plus n cubed. That's what it means, right? It's I squared, and I cubed. Okay. Our next step is to look at a graph. Give me a simple graph, a simple function. F of x, a quadratic function. I don't know, let's say x squared plus 1. Give me an interval, a nice interval that starts with 0. Let's say 0 to 4. And here's the question. I'm going to graph the function, and I would like to determine the area, find the area under f of x between 0 and 4. Okay. So this is 1, this is 2, this is 3, this is 4. However, 4 squared plus 1, so 0 is here. 0 plus 1 will be here. 4 squared plus 1 is 17. And I'm going to say that 17 is here. And this is the graph of f of x, which is x squared plus 1. And here is the area under the graph. I want to find this. Find this area. Okay. I don't know how to determine this area yet. So I'm going to approximate it. The area using 4 subintervals. in three different ways. Area left, area right, and area mid. So left most point, right most point, mid point. What's all this? I'm going to graph my function one more time. I'm going to graph it better this time. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Okay. This is the graph. And I'm going to divide the interval 0 to 4, as I was told, using 4 equal subintervals. And obviously, the width of the interval is 1. And I'm asked to use and approximate the area using the leftmost point. Okay, I'm going to create a rectangle using the height from the leftmost point. And get this. I'm going to use for the next one, as I was told, for the left, using the leftmost point for the height. And I'm going to determine this rectangle, the area of that rectangle. Then I move on to the next one, and I have to use the height using the leftmost point. So this will be the next subinterval. And now the last one, I'm using the leftmost point, and I'm determining this area. Now here's a question for you. Will this area, this approximation of the orange, blue, whatever that is, gold, and black, when I add these 4 areas, will I get a underestimated or an overestimated value of the correct and the exact area? Will it be an underestimation or an overestimation? Right, because look, I did not account for this or this or this or this. So I will say the area with 4 left is approximately base times height, 1 times f of 1, f of 0, 1 times f of 0, plus base times height, for the blue one, base times height, 1 times f of 1, plus for the gold, base times height, plus 1 times f of 2, plus, last one, base times height, 1 times f of 3. I will factor out the 1 from all of them. So then I will have f of 0. Remember the function was x squared plus 1. So f of 0 will be 1 plus f of 1 will be 2 plus f of 3 will be 10 plus f of 0 was 1, f of 1 is 2. I missed this one, 5 plus 10. So this will be 18. Are we happy with this approximation? It's something if I don't have anything, but it's not a good approximation. Agreed? Okay. I will repeat now. This gave us 18. So this one, 18. I will repeat the process with the rightmost point. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. This time, the same situation, except that this time I'm asked to use the rightmost point for each subinterval. Okay, this is the rightmost point. This is the rightmost point. This is the rightmost point. And here's the last one with the rightmost point. So the area right with 4 will be approximately base times height, 1 times f of 1, 1, 2, 3, 4, plus base times height times f of 2, plus 1 times f of 3, and plus 1 times f of 4. Because now I'm using the rightmost point. I factor out 1, I don't have to worry about that. F of 1, I already had it here. F of 1 is 2 plus 5 plus 10 plus f of 4, which is 17. That's how I keep getting to 17. So this is 17 plus 17, which is 34. So we got this as being 34 as the area. Do you like 34? No, of course, nobody likes 34. We know, and we don't like 18 either. Correct? Good. Okay, so now I'm going to determine the area with a midpoint with 4 subintervals. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Good. This time, I want to find the area using the midpoint with 4. Look what happens now. Okay. Midpoint, height, rectangle. Midpoint, I need a different color. Midpoint, height, rectangle. Midpoint, height, rectangle. And finally, midpoint, height, rectangle. Will this be the best approximation of the area under the graph of x squared plus 1 using 4 rectangles or not? Of course. Still base times height. So approximately 1 times f of between 0 and 1 is f of 0.5 plus base times height. This is now between 1 and 2, so this is 1.5. F of 1.5 plus base times height. This is between 2 and 3, so it's 2.5 plus the last one, 1 times f of 3.5. So with the graphing calculator, here's what I recommend. In lists, I want to edit a list. So my list is 0.5, 1.5, 2.5, and 3.5. My next list will be a function, because I want to determine a function of all these numbers in a blink. And the function is x squared, I'm sorry, it's L squared, L1. L1, oh, I didn't mean that. Okay, so go highlight L2 and this is L1 right here, second and L1 squared, that's our function, and I want it to be applied to every number in L1 plus 1. And I hit enter, and I get all those answers. How do I sum them up without adding them up by hand? Here's how I do it. I go to stats. I want to calculate. I want one variable statistics on list L2. I'll do this more than once. And I want to calculate. And you will give me the sum. You know now this notation, right? Look at it. Sum of x. It added up all the x's in list L2, and the sum is 25. So I'll show this again in a second. So coming back to our answer. This is far from being exact. But which of these three numbers you would prefer or accept? 25. You will accept with 4 subintervals. This is a huge, it still has huge error. Why? Because I only used 4 subintervals. What if I go from 4 to 8? Will that be a better approximation? I'll show you that what I just did with the list in a second. Will that be a better approximation if I used 8? Okay. What if I use 16? Will that be a better approximation? What if I use 32? Would that be a better approximation? What if I use 64? What if I use 128? What concept is this that we discussed in this course? Say it again? No. Something else from before, from the very beginning. When I increased from 16 to 32 to 64 to 128, what is this? What am I trying to do? I'm trying to find a limit. That's exactly what I'm trying to do. So I will say this. As the number of subintervals increases to, what do you think it should increase to? To make sure that I have no gaps ever in the area. What should it increase to? Of course. As the number of subintervals increases to infinity, we will have, say it again. Right, it will be the best. Once I have the limit, as n goes to infinity, n being the number of subintervals, n number of subintervals. And now let's construct this together. The limit of what? So when I had 4 subintervals, I had 1, 2, 3, 4 additions of areas. Base times height, base times height, base times height, base times height. Right? Now I increased that number to infinity. So how many terms will I have when I increase 4 to infinity? Infinity, right? Okay, perfect. So that's awesome. Now what? How do I write 1 times the function plus 1 times the function evaluated at blah, 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 plus 1 times the function plus 1 times the function? We just learned a notation an hour ago. What notation is that? That will allow me to, instead of saying to you 1 times f of x plus 1 times the other f of x plus 1 times the other f of x plus 1 times the other f of x plus 1 plus 1 plus 1. What notation? Of what? Exactly. Okay, stay with me. Very good. So now, what am I adding here? So this is definitely a sum. But what is this? Because it has to be here. And what is this? Because I have to put it here.
So 1 times.
So this is what it's called delta x. So delta x is the width of each what? Subinterval, right? This is the width of each subinterval. Here I had 4 subintervals, so this was, the width was 1. Okay. Now, times what? F, very good. F, I'm going to put x star, and I'll explain what star means. It could be the leftmost point, it could be the rightmost point, or it could be the midpoint. But we have to determine it. So that's why bear with me and use the star. Okay? And of course, I also have to put an I in there. Why? Why do I put xi? See, this does not change. It's delta x. But this changes from 0.5 to 1.5 to 2.5 to 3.5. So that's why this is not just x. It's xi star. From I equals 1, from the very first subinterval till the last one. What is the last one? Say it again. For 4 is true. But we are looking at as the number of subintervals increases to infinity. So, and n is the number of subintervals. So this is n. And n will increase to infinity. Now, question. Can I put the equal symbol now? Or still approximation? That's my question. Between this and this, can now with certainty put the equal symbol, or it still has to be approximate? So before you answer, I have n subintervals, and they increase to infinity of what? Base times height plus base times height plus base times height plus base times height, and I fill them up. I fill up the entire area with infinitely many subintervals. Will this be still approximate or definitely equal? Say it again. It's definitely equal. If I go to infinity, there is nothing left to fill in. I can. You will see in a minute. Of course we can.
But how? It never ends.
True. In other words, when n approaches infinity, you will be able to determine this limit.
Oh, yeah. The limit's not.
Right. The limit will take care of that. Okay. This bears the name of the mathematician who came up with it. His name is Riemann. And of course, is Riemann sum. Of course, Riemann sum. And of course, the area equals the limit of the Riemann sum. And it definitely equals. There is no approximation symbol here needed anymore. What I would like you to do between now and Monday is determine and perform all the calculations for these 4 subintervals, 8 subintervals, 16, and also if you can 100, you have to estimate it. Of course, you're not going to do 100. I don't expect you to. And the same thing here. And I want you to come up with your best approximation here, or estimate. And 16, 12, and 24. And the same thing for this function. And find the area between 0 and pi over 2. And for this function, and find the area between 0 and 2. Because now I want to show you something else. So please fill up these tables. So of course this is rightmost with 4, with 8, 16, and 100. leftmost with 4, 8, 16, and 100, and then midpoint with 4, 6, 8, 16, and 100. I want to see what you come up with. And now I would like to show how to determine this area exact, right? We looked at 18, we got 32, and we got 25 in the middle. Okay, do I still have time? No, I don't, I'm sorry. Okay. So remind me 3 things I will not forget. Once I tell you that, to remind me, then I will not forget.